Let's explore the fascinating pattern behind adding up consecutive natural numbers, a concept that appears throughout mathematics and everyday problem solving. Natural numbers are simply the counting numbers we use every day: 1, 2, 3, 4, 5, and so on. We'll be looking at what happens when we add these numbers in sequence. Let's start with simple examples. The sum of just the first natural number is trivial. It's just 1 by itself. When we add the first two natural numbers, 1 plus 2, we get 3. For the first three natural numbers, we have 1 plus 2 plus 3, which equals 6. Notice how our sum is growing faster as we add larger numbers. Adding the first four natural numbers gives us 1 plus 2 plus 3 plus 4, which equals 10. Is there a pattern forming here? 1, 3, 6, 10. But what if we wanted to find the sum of the first 100 natural numbers? Adding these numbers one by one would be time-consuming and prone to errors. We need a more efficient approach, a formula that works for any number. To discover this formula, let's visualize these sums as triangular arrays of dots. Each row will represent the next natural number in our sequence. Our first row has just one dot, representing the number 1. The second row has 2 dots, representing the number 2. The third row contains 3 dots, and so on. Notice how we're building a triangular shape. This triangular arrangement of dots gives us a visual representation of our sum. Mathematicians like Carl Friedrich Gauss recognize that these triangular numbers follow a specific pattern that can be captured by a formula. The formula turns out to be n times n plus 1 divided by 2, where n is the number of terms we're summing. This elegant formula calculates the sum of the first n natural numbers instantly. With this formula, we can find the sum of any number of consecutive natural numbers without having to add them individually. For example, to find the sum of the first 100 numbers, we would calculate 100 times 101 divided by 2, which equals 5,050. Now that we've seen the pattern and the formula, let's prepare to explore how this formula can be derived and why it works. The sum of the first n natural numbers can be written using sigma notation as the sum from I equals 1 to n of I. Our goal is to find a closed formula for this summation. Let's explore how the young mathematician Carl Friedrich Gauss developed a brilliant shortcut for finding the sum of the first n natural numbers. Imagine we want to find the sum s of all numbers from 1 to n. Writing it out, we get s equals 1 plus 2 plus 3, and so on, all the way up to n. Adding these numbers one by one would be quite tedious, especially for large values of n. Here's where Gauss's insight comes in. He realized we could write this same sum in reverse order, s equals n plus n minus 1 plus n minus 2, continuing all the way down to 1. Since we're just reordering the terms, this sum equals the original sum. Now comes the clever part. Instead of adding each sum separately, let's look at what happens when we pair corresponding terms from both expressions. Let's take the first term from each sum, 1 from our first sum and n from our second sum. When added together, these give us 1 plus n, which equals n plus 1. Moving to the second terms, we have 2 from the first sum and n minus 1 from the second sum. Adding these together gives us 2 plus n minus 1, which simplifies to n plus 1 again. For the third terms, we pair 3 with n minus 2. Adding them gives us 3 plus n minus 2, which again equals n plus 1. Do you see the pattern forming? Every pair of corresponding terms from both sums always adds up to exactly n plus 1. The first number increases while the second number decreases by the same amount, keeping their sum constant. This pattern continues for all pairs of terms, all the way to the last pair, n from the first sum and 1 from the second sum, which also gives us n plus 1. Since we're pairing each number from 1 to n with its counterpart, we have exactly n pairs in total. And as we've seen, each of these n pairs sums to n plus 1. Now here's the key insight. If we add both of our expressions for s together, we're essentially adding all these n pairs. Since each s contains all terms from 1 to n, adding them gives us 2s. And since we have n pairs, each summing to n plus 1, our total is n times n plus 1. Finally, to find s alone, we divide both sides by 2. This gives us our elegant formula, s equals n times n plus 1 divided by 2. This is the formula for the sum of the first n natural numbers. With this formula, we can now quickly calculate the sum of any sequence of consecutive natural numbers. For example, to find the sum of numbers from 1 to 100, we just plug in n equals 100, giving us 100 times 101 divided by 2, which equals 5050. Gauss's method teaches us that sometimes approaching a problem from a different angle can reveal patterns that simplify complex calculations. By pairing terms strategically, we discovered a simple formula for summing natural numbers. Let's derive the formula for the sum of the first n natural numbers. We want to find a simple way to calculate 1 plus 2 plus 3 and so on, all the way up to any number n. There's a clever approach we can use to find this sum without adding all the numbers individually. We'll write the sum in two different ways and then combine them. Here's our original sum s. Now let's write this same sum again, but in reverse order, starting from n and going backwards to 1. The value doesn't change, it's still s, because we're adding the same numbers, just in a different order. Let's look at what happens when we pair up corresponding terms from both sums. The first term from the top row and the first term from the bottom row give us 1 plus n. The second terms give us 2 plus n minus 1. The third terms give us 3 plus n minus 2. Each pair always adds up to n plus 1. This pattern is quite powerful. We can see that every pair sums to exactly n plus 1. And how many such pairs do we have? We have exactly n pairs, because there are n numbers in our original sum. Now, if we add both of our equations together, the left side gives us s plus s, or 2s. The right side gives us n pairs, each summing to n plus 1. That's n times n plus 1. Let's simplify this equation. S plus s equals 2s, so we have 2s equals n times n plus 1. To solve for s, we need to divide both sides of the equation by 2. On the left, 2s divided by 2 gives us just s. On the right, n times n plus 1 divided by 2 gives us our formula. We've now derived the formula for the sum of the first n natural numbers. It equals n times n plus 1 divided by 2, or n times n plus 1 over 2. This elegant formula lets us quickly find the sum of any sequence of consecutive natural numbers starting from 1. For example, if we want to add the numbers from 1 to 100, we can use n equals 100 in our formula, giving us 100 times 101 divided by 2, which equals 5050. Let's explore a fascinating pattern by visualizing the sum of the first 5 natural numbers using dots arranged in a triangular pattern. We'll start by creating a triangle where the first row has 1 dot representing the number 1. The second row has 2 dots representing the number 2. The third row has 3 dots, the fourth row has 4 dots, and the fifth row has 5 dots. This triangular arrangement represents the sum we want to calculate: 1 plus 2 plus 3 plus 4 plus 5. If we count all these dots, we would get the answer. But we want to find a formula that works for any number of terms. In the general case, this triangle represents the sum of the first n natural numbers, where n could be any positive integer. Here's where the clever geometric insight comes in. We'll make an identical copy of our triangle, color it blue, and flip it horizontally to create a mirror image. Now we'll position this blue triangle right next to our original orange triangle. Notice how they fit together perfectly. When we place the two triangles together, they form a rectangle. Let's add lines to highlight this rectangular shape. Looking at the dimensions of our rectangle, the width is 5, which equals our value of n, and the height is 6, which equals n plus 1. This is because each column contains dots from both triangles that add up to n plus 1. The area of this rectangle can be calculated by multiplying its width by its height. That gives us n times n plus 1, which in our example is 5 times 6, equaling 30 dots total. But remember, we created two identical triangles. The original sum we're looking for is represented by just the orange triangle, which is exactly half of the rectangle. So we divide the total area by 2. This gives us our final formula. The sum of the first n natural numbers equals n times n plus 1 divided by 2. For our example with n equals 5, that's 5 times 6 divided by 2, which equals 15. This elegant formula, read as the sum from I equals 1 to n of I equals n times n plus 1 divided by 2, gives us a direct way to calculate the sum without having to add all the numbers individually. You can verify this works for any value of n. The power of this geometric approach is that it helps us see why the formula works, not just memorize it. This same visualization technique can be applied to many other mathematical problems. The sum of the first n natural numbers can be found using this elegant formula. It states that the sum from I equals 1 to n equals n times n plus 1 divided by 2. Let's verify this formula is correct by testing it with a specific example, finding the sum of the first 10 natural numbers. We'll substitute n equals 10 into our formula. So we're looking for the sum from I equals 1 to 10 of I, which according to our formula should equal 10 times 10 plus 1 divided by 2. Now let's solve the right side of the equation step by step to find the numerical value. First, we calculate what's inside the parentheses. 10 plus 1 equals 11. Next, we multiply 10 by 11. 10 times 11 equals 110. Finally, we divide 110 by 2. This gives us our answer, 55. So according to our formula, the sum of the first 10 natural numbers should be 55. But is this actually correct? Let's double check by calculating the sum directly, adding each number from 1 to 10 one by one. We want to verify that the sum from 1 to 10 equals 55, as our formula predicted. Let's write out all the numbers from 1 to 10 that we need to add together. To make this clearer, let's calculate the running total as we add each number. Let's start with some smaller sums. 1 equals 1. 1 plus 2 equals 3. 1 plus 2 plus 3 equals 6. 1 plus 2 plus 3 plus 4 equals 10. As we continue adding each new number, the sum grows according to a pattern. If we kept going, we'd see that each new number contributes exactly its value to the running total. Continuing this process all the way to 10, we add 1 plus 2 plus 3 and so on until 10, giving us a total of 55. Look at that! We get exactly 55, which perfectly matches what our formula predicted. This isn't a coincidence. It works because the formula is correct. This confirms that our formula works for n equals 10. The sum of the first 10 natural numbers equals 10 times 11 divided by 2, which is 55. This formula works for any value of n, not just 10. The formula for the sum of the first n natural numbers is elegantly expressed as n times n plus 1 divided by 2. This simple formula saves us from having to add up all the numbers manually every time. Let's explore some fascinating real-world applications of our sum formula n times n plus 1 divided by 2. These examples will show how this mathematical concept appears in everyday situations. Our first example is the classic handshake problem. Imagine 5 people meeting at a gathering. If each person shakes hands exactly once with everyone else in the room, how many total handshakes will occur? This is a perfect application of our summation formula. Here we have 5 people arranged in a circle. To solve this problem, we need to count how many unique pairs of people can form to shake hands. Let's visualize each handshake. The first person needs to shake hands with the other 4 people. The second person has already shaken hands with the first, so they only need to shake hands with the remaining 3 people. Do you see the pattern forming? After counting all possible handshakes, we find that 5 people will have a total of 10 handshakes. This makes sense because each person shakes hands with everyone else without repeating any handshakes. We can calculate this directly using our formula. With 5 people, the number of handshakes equals 5 times 4 divided by 2, which equals 10. The reason we divide by 2 is because each handshake involves exactly 2 people, and we don't want to count the same handshake twice. Generalizing this to n people, the total number of handshakes is given by n times n minus 1 divided by 2. This is because each person shakes hands with n minus 1 other people, but we divide by 2 to avoid double counting the same handshake. This formula is actually a variation of our sum formula. It represents the sum of the first n minus 1 natural numbers, which is 1 plus 2 plus 3, and so on, up to n minus 1. This pattern shows up because the first person shakes hands with n minus 1 people, the second with n minus 2 people, and so forth. Now let's explore another practical application of this same formula in a different context. Our second example involves tournament scheduling. Imagine a round-robin tournament with 6 teams, where each team must play against every other team exactly once. How many total games need to be scheduled? This is another perfect application of our summation formula. Here we have 6 teams arranged in a hexagon. Each team needs to play against every other team exactly once during the tournament. This is very similar to our handshake problem, where instead of people shaking hands, teams are playing matches against each other. Let's visualize all the required matches. The first team needs to play against the other 5 teams. The second team has already played against the first team, so they need to play against the remaining 4 teams. The pattern continues just like in our handshake example. After mapping out all the required games, we find that a 6-team tournament needs exactly 15 matches to ensure every team plays against every other team once. This is the minimum number of games needed for a complete round-robin tournament. Using our formula, we can calculate this directly. For 6 teams, the number of matches equals 6 times 5 divided by 2, which equals 15. Each team plays against 5 other teams, giving us 6 times 5 total team matches, but we divide by 2 because each match involves exactly 2 teams. For any number n of teams in a round-robin tournament, the total number of matches needed is n times n minus 1 divided by 2. This is the same formula we derived for the handshake problem, showing how the same mathematical pattern appears in different scenarios. Both of these examples demonstrate how our sum formula applies to real-world counting problems. Whether we're counting handshakes, tournament matches, or many other similar scenarios, the formula n times n minus 1 divided by 2 gives us the total number of unique pairs that can be formed from n items.